All right, let's go ahead and get started. Our next speaker is Dr. Fangchan Zhang from Montana State University. He works in the cybersecurity lab there with Dr. Adversarial, who gave us the hands-on demo last week related to digital forensics. So thank you for joining us, Dr. Zhang, and the show is yours.
Okay, thanks for the invitation. So before our presentation, I will briefly introduce myself. My name is Fangchan Zhang. I'm a assistant professor at the Montana State University. I received my PhD from the George Washington University and received my postdoc training from the Pennsylvania State University and the University of Notre Dame. And my research primarily focuses on software security, program analysis, and machine learning for cybersecurity. I'm very open for collaboration. And the topic I'm going to present today is the practical adversarial mock example attacks and defenses. And it will be presented around 3 sections. In the first section, I will briefly introduce the software security. In the second section, I will present a framework that can produce adversarial mock examples to attack antivirus products in the real world. And in the last section, I will propose a solution to defending adversarial malware examples. So let's start with the question: who needs to worry about software security?
We are not seeing your presentation. We're just seeing the cover slide.
Ah, okay. So can you hear?
No, we're seeing like the PowerPoint, not the presentation of it.
We're seeing the editor.
Oh, okay. So let me try. Still working right now?
No, it didn't change.
Oh, okay. That's weird. So I can oh, okay. Okay, thank you. So in the first section, I will briefly introduce software security. And in the second section, I will present a framework that can produce adversarial examples to attack antivirus products in the real world. And in the last section, I will propose a solution to defending adversarial examples. So let's start with the question: who needs to worry about the software security? So software engineers or researchers. So because their jobs are to guarantee the software security. Actually, everybody should worry about your software security nowadays. So you can easily access to your bank records, medical records, and credit card information via software. If the software is not secure, so it's gonna cause many problems, such as the identity theft, loss of data, denial of service, and even financial loss. And there are 4 major types of software security issues, such as the malware attack, software vulnerability exploitation, denial of service attack, and a linearization attack. Linearization attack is to use the crypto analysis techniques to recover the encrypted information, so causing the personal information leakage. And my presentation is related to the malware attack. And then I'm gonna propose a framework that can name the malfolks so that I can produce adversarial malware examples to attack antivirus products in VirusTotal with high confidence. So the framework just simulates the rival games between the antivirus products and the malware. And why did I conduct such research? I was attracted by a couple of examples. For example, in image recognition, an image is recognized by the machine learning system as a bobcat. It does, right? And so after it is perturbed to become an adversarial example, the same machine learning system just recognizes it as a hippo. They're totally different, but we as a human can still recognize it. And image in speech recognition and audio is translated by the machine learning system into the software security. After it is added with the noise to become an adversarial example, the same machine learning system just translates into program analysis. So I'm wondering if it is possible for a malware that is detected by a set of like malware detectors as the malicious to be processed by perturbation module to become an adversarial example. The same set of adversarial example, same set of malware detectors cannot detect it. To generate the practical adversarial examples, there are three major challenges. Like first, we have to instrument the malware samples to attach perturbation. Second, we have to remain the functionality of originally like malware samples. So that is, we have to keep the functionality unchanged. Otherwise, they may not be the malware anymore. And third, so they should be able to evade the detection by malware detectors on their black box setting because they don't open source their codes. We have no ideas of their implementations. So then we propose our framework. The framework consists of 5 major components. Each component has a certain functionality. For example, p-parser retrieves the dynamic link libraries and the system functions in programs as features. And generator produces a perturbation path that improves the malware's evasive capability while maximizing the probability of discriminator making a mistake. And p-editor follows the perturbation path to produce an adversarial example. And discriminator estimates the probability of maliciousness for a malware program and provides gradient information to train generator. And detector ensures the reliability of datasets, provides labels for discriminator, and validates the performance of malfolks. In general, discriminator is to have some decision boundary as detector, and the framework is trained to produce adversarial mock samples that can first evade the detection by discriminator and then evade the detection by the detector. And the detector is the real world antivirus products we want to attack. And then, so I'm gonna show you how to train the framework. First, the malware and the binaryware are sent to p-parser for feature extraction, and then sample mini batch of a malware concatenated with Gaussian noises as input to generator. Gaussian noises here is the help to train the framework and trying to produce diverse perturbation paths. And the generator here gonna produce the perturbation path, which will be followed by the p-editor to generate adversarial examples. And then sample another mini batch of binaryware and use the binaryware and adversarial examples to train the discriminator and updates its parameters. And then we're gonna sample another Gaussian noises, combine the malware with the Gaussian noises as input to generator, which outputs a perturbation path. p-editor follows the perturbation path to produce the adversarial examples, which are sent to detector for labeling. And then we train the generator and updates its parameters with the help of a discriminator. And after the framework is well trained, so it can be used to generate a powerful adversarial example. For example, given malware, the p-parser extracts its features, and the features will be combined with the Gaussian noise as input to the generator. So it outputs a perturbation path. p-editor just follows the perturbation path to generate an adversarial example. And then, so I'm gonna show you how to implement each of the components. The first component is the p-parser. p-parser is used to extract like deal names and system function names as features. To extract deal names and system function names, we have to know the structure for Windows program. Each Windows program gonna follow the P format. It has like 6 pieces. Each piece will be located at a certain offset from the beginning of the program file. To locate the deal names first we have to locate the data directories. Data directories has 16 tables. Among them, import and IT tables can be used to extract DO names. Here we take import as example. The import table has two fields, the virtual address and size. Virtual address is an address that points to an array of import descriptors. Each import descriptor is the structure, and it has multiple fields. And here we're gonna use the field name. Name is an address that points to the name of a deal. To extract the system function names, we should also allocate the data directories and then import table. And import table just point to an array of import descriptor. And here we use the field original first thunk. Original first thunk is an address that point to an array of INT table. Each INT table has two fields. And here we're gonna use the field name. Name is an address that points to the name of a system function. And finally, we extracted of the deal names and system function names. And because deal names and system function names are strongly related to the functionality of a malware, so we could use them as a feature to represent the malware and trying to look for the optimal solution to obfuscate them. And finally, they can evade the detection by real-world antivirus products with a high confidence. And then generators. Generator is the convolutional neural network. So it has 13 layers in total, including 40 connected feed-forward layers, convolutional layers, dropout layers, and upsampling layers. The third component is the P editor. It implements three obfuscation perturbation methods. The first perturbation method is called obfusmal. It consists of two components, the malware with encrypted code section and the shared.dl. To develop it, first it reads the malware, obtain the address and size of the code section, and encrypts the code section. And then develop shared.dl with the functionality that can store the crucial information, such as the size and address of the code section and the key, and decrypt the code section and jump to the start address of the program execution for the malware to execute it. And finally, so we're gonna add a section in the malware to save shared.dl. To execute it, the OEP will be directed to the shared.dl. Shared.dl will decrypt the code section and jump to the OEP of the program. And the OEP is the start address of a program execution. The second method is called the steal mode. It consists of two components, share.exe and encrypt the malware. And to develop it, so we first encrypt the entire malware and then develop a program named share.exe with the functionality that can decrypt the malware, create a suspended process, obtain the process space, copy the decrypted malware to the space, and change the process context to the OEP of the malware, and add another section in the share.exe to save the encrypted malware. And to execute it, first the OEP is directed to share.exe. Share.exe will decrypt the malware and create the process context for the malware to execute. The third perturbation method is called hollow mode. It consists of three components: binaryware, encrypted malware, and the hollow.dl. The binaryware here is used to enhance the concealment of encrypted malware. And to develop it, first, we're gonna select the binaryware, encrypt the entire malware, and add a section in the binaryware to save the encrypted malware. And then we're gonna develop hollow.dl with the functionality similar to the share.exe. and add another section in the benign to save the hollow.dl, just follow in the encrypted malware. To execute it, the OEP is directed to hollow.dl first. The hollow.dl will decrypt the encrypted malware and create the process context for it to execute. And they can also be combined. And here we take the Adversarial and Steelmo as example. So it consists of 3 components. To execute it, first the OEP is directed to share.exe. Share.exe will decrypt the intermediate adversarial example. So that is the second and the third component here. And then create the process context for it to execute. After it is executed, it will be directed to share.dl. Share.dl will decrypt the code section and jump to the OEP of the code section. And finally, the malware is executed. And then we use the VirusTotal as the detector because it contains many antivirus products and online scan engines to check for malware, and popular tools such as McAfee F-Secure and Microsoft have been widely adopted on laptop and mobile devices. And it is well received by the security professionalists and researchers. And the discriminator is also a convolutional neural network. It has like 15 layers in total. And the difference between the discriminator and the generator is that it contains the it didn't contain the upsampling layer, just contains the convolutional layer. And finally, we're gonna evaluate the performance of Malfolks via discriminator and the detector. And we first take the discriminator as the tag target and evaluate via the accuracy. The accuracy is the ratio of incorrectly predicted adversarial examples over all adversarial examples. The higher of the accuracy, the better of the performance. So as shown in the table, Malfolks achieves the highest accuracy in both the trained dataset and tested dataset. So achieving at 99%. And then we take the VirusTotal as the tag target and evaluate via the detection rate and the evasive rate. The detection rate is the ratio of entities that detect the malware or adversarial example over all entities. Evasive rate is the ratio of entities that detect the malware but failed to detect the adversarial example. The lower of the detection rate, the higher of the evasive rate, and the better of the performance. As suggested by the table, the average detection rate for the malware is lowered from 68.8% to 29.7%. Correspondingly, the average evasive rate is reaching to 56.2%. So that means a majority of malware detectors in VirusTotal has been defeated. And after the generation of adversarial examples, so existing malware detectors based on classification, either static-based or dynamic-based, should be improved. They have major weaknesses. For example, static-based classification has high knowledge barriers for security engineers, but they should have the background knowledge to understand the programs before they can analyze the program. And it has the complicated performance examination and infeasible reverse analysis for encrypted or compressed malware. While the dynamic-based classification has high computing burdens for computers, so you have to iterate every execution path to collect their behaviors and to collect their traffics. And it has a poor reliability due to specific inputs and a complicated performance examination. Our goal is to provide an efficient but simple classifier to distinguish different types of adversarial examples as well as other types of malware samples. And to provide an efficient, simple, and effective defense strategy, we have to deal with the processing time for classification that should be withstood by the users. And it should correctly distinguish different malware families, although encrypted or compressed. And it should provide a simple method of validating the defensive performance for users. And then we're gonna propose the framework, it's called a Vismo, because our goal is to look for the similar set of instructions. If we directly disassemble the binary into instructions and build a graph to look for these instructions, so the efficiency is a major concern. So we turn to use the machine learning and because there is a direct mapping between the instructions and the bytecode. So we decide to convert the malware samples into images. And because the CNN is pretty good at capturing the similarities in images. So we finally decide to use the CNN to classify the malware images. And so first, the framework will convert the malware samples into images. And then we will apply contrast limited adaptive histogram equalization algorithm to images in order to enhance the similarities for malware samples belonging to the same family. And then they will be resized to a smaller size and before being fed into the CNN for final classification. And so then I'm gonna show you how to implement each of the components. First, the converter will convert the malware samples into images. First, it will sequentially read the binary data in bytes and convert each byte into number ranging in 0 to 255. And then it's gonna reshape the image data by flowing a recommended fixed width with the variable height, so given in the table. And then, so we're gonna use the feature engineer to enhance the similarities for malware samples belonging to the same family, because each instruction is correlated with each other. So we decide to transform the instructions to have a linear relationship. And so first we have to denote like a CDF. CDF is short for cumulative distribution frequency, and it counts the the cumulative frequency for for the bytecode. So that is also the pixels. And CDF 0 indicates the frequency of a pixel 0, and CDF 1 counts the sum of frequency for pixel 0 and pixel 1. And then so we can use the different transformation methods to transfer them. Like first, for the pixels in the region, like purple, so they will be transformed by the formula 2. And for the regions so for the nine blue regions, so the pixels gonna be transformed by following the formula 3. And for the pixels in the pink region, so they're gonna be transformed by following the formula 4, 5, and 6. And since there are some paddings between the code sections and the data sections, so we decide to use the clipping technique to spread their frequencies into different pixel values. And the classifier uses the CNN to classify an image. And finally, we're gonna evaluate the performance of Vismo via the precision, recall, F1 score, and accuracy. So as suggested in the table, the Vismo achieves a pretty high accuracy compared to other existing methods, so which is over 95%. And the framework can also classify a malware at 4 milliseconds on average, so which is the factor 1 compared to other methods. And we also provide a very simple way to validate the effectiveness of the framework. So after the malware images processed by our algorithm, malware samples belonging to the same family will have pretty similar textures. And for malware samples belonging to the different families, they're gonna have very different textures. Yeah, thanks for your listening. So any questions?
Plenty of time for questions. Anybody have one? All right, well, thank you, Dr. Zhang. Looks like we don't have any questions on our end here, so.
Yeah,
Yeah, it's a great talk.
thank you so much.